Okay, so Dr. Cinco talked a lot about center of mass, and so we'll go past. We do want to focus on Newton's second law for rotating objects and talk about how that same F equals ma is going to work for rotating things. And in the absence of a net force, we don't have anything that accelerates. And the same kind of thing with this, if we don't have a net torque, the rotating object will not rotate. Now we do need to talk a little bit about moment of inertia, and I know Dr. Cinco did that. It looks like the Greek letters did not come through here. Okay, this is just kind of showing where these formulas are coming from. And I think he derived at least one of them, maybe the bar swinging around an axis on the end. I think he derived that one. So you kind of know where these are coming from. But we have these moments of inertia. Formulas are here. And the one I think we were talking about in class and derived in class was that one. But any of these you can kind of take a look at and see that we could get the same thing by doing the same process. If you're ever wondering what the moment of inertia for something would be, you can always ask me. I suppose you could derive it yourself, or you could kind of guess what would work there. Some examples of changing moments of inertia, is the farther the mass is away from the rotation, the more rotational inertia it will have. So some really good examples here. Well, we showed that one in class. A tightrope walker using a long pole, but even if you're trying to walk in a straight line, you put your hands out sometimes just to kind of keep yourself from rotating. Well, that's what you're basically doing there is you're taking your mass and you're moving it farther away from your rotational area, the axis of rotation, and so you're not going to rotate as easily. Person runs with their legs bent because they want to go faster. They don't want as much rotational inertia, so they keep their legs close to their body. A short pendulum will swing faster than a long one because a long one has that mass distributed farther away and will have more inertia, less willingness to rotate. And I think Dr. Cinco talked about the industrial flywheel idea. Okay, the formula for this is going to be torque is going to equal moment of inertia times rotational acceleration, which makes sense because if you did force is equal to mass times acceleration, what we're going to do is we're going to apply a torque, which is a force times lever arm, and we're going to, instead of mass, we're going to do moment of inertia. So that's mass times, or taking into consideration where that mass is located around the axis of rotation. And instead of A, we're doing alpha. So this Newton's second law makes sense. And so again, choose a moment of inertia or calculate a moment of inertia and use that. You can always ask me too. All right, so we're just going to do a couple of examples here. And we have a catapult and the radius of 0.35 meters. So we're going to probably do a point mass about an axis. This is not a uniform mass. It's a longer arm, and then it has a bigger mass here. So we're going to go ahead and use a point mass. So the moment of inertia is going to equal mr squared. I have a dog here that just will not leave me alone. Okay, stop. Okay, just stop. All right, so the mass is a 0.150 kilogram stone. The radius is 0.35 meters, or square that. We're going to get a moment of inertia of 0.018 kilogram meter squared. The tangential acceleration is 100 meters per second squared, but of course we need alpha, so we're going to go ahead and take that 100 and divide it by 0.35, and we're going to get 286 radians per second squared. And then the torque is going to equal 0.018 times 286. We'll get 5.14 Newton meters of torque. Pretty easy. The next example, we have a toy hoop, and don't know what's going here. Okay, this toy hoop is, I don't know why that example is down like that. Okay, whatever. Let's see, we'll zoom it. Yeah, there we go. We've got a 165 gram toy hoop with a 13.5 centimeter radius rotating. So if you look at your moments of inertia, if you have a hoop, moment of inertia again will be mr squared. And we're going to get 0.165 kilograms times 0.135 meters. And we're going to get 0.003 kilogram meter squared. Okay, and then sometimes we have to go back and use some angular kinematics. And so it's going to stop, but it was going at 30 radians per second, and it's going to stop in 0.1 second. And so your angular acceleration is going to be negative 300 radians per second squared. Then your torque is going to equal your I times your alpha. And you're going to get negative 0.900 Newton meters of torque. Now it says what force is exerted on the hoop. Make sure you realize that force, it's a hoop, right? So this force that's being applied right here, the radius is the lever arm. So we're going to go force times lever arm, which in this case is just the radius, is going to equal torque. So we just solve for the force being a negative 6.7 newtons of force. Okay, I actually do that wrong. It would be a negative torque, so the force would be over here, but you get the idea.